All right, 3 o'clock. Welcome back to the very last installment, minus your final exam, of your favorite class. All right. So here we are, 3 o'clock, our regular meeting time. Time for the last installment. But it's not the last time you're going to see my face. Hopefully, you signed up for my composites class or you signed up for 3005 with me. So it's not going to be the last RAR you ever hear. RAR! All right? Hopefully it's not. All right. So yeah, if you're new, you just kind of joined the stream. Here we have a student submitted meme. When you know it's the last time you hear them say "rar." It's funny. That was a student submitted meme. It was someone from my composites class that I'm teaching right now, but I still thought it was pretty funny. So what do we got going on? All right. Today we're gonna finish our review for exam number 3, and then tomorrow you're gonna take exam number 3, and you're gonna dominate it and crush it like a grape and kick it into high gear and crush it like a little peanut. All right? Right? Yes, of course. So exam number 3 in class. Make sure also do your instructor evaluations. You can finally get back at me for the terrible handwriting and yelling into the microphone, "Rawr!" etc. Okay? There you go. So what did we do yesterday? Well, yesterday we did impulse and momentum problems from our exam review sheet. So here's our exam review sheet. We did problem number 1, which looked at the radius of gyration and the angular velocity of a wheel after it's been spun up with some certain moment applied to it. So we looked at a time-dependent moment that was being applied, and we figured out the angular velocity of this particular thing using conservation of momentum. That was kind of like our warm-up. Brushed our shoulders off, and then we went on to number 4, looking at a little bit more complicated problem where you had a bullet striking a pendulum. What happens to the angular velocity of that pendulum right after the bullet strikes? Okay, so there's a momentum. There will be a momentum problem on the test. Hopefully you're not surprised by that, but I'm just giving you that one. All right, there's going to be a momentum problem on the test. The other 2 problems on the test, one will be on linkages, which looks like, this little guy, which you're all too familiar with now after doing your simulation and all the hand calculations required. And there will be one question on gears, gearing system, and gear trains. All right, so there you go. That's information about the test. 3 problems. All right. Any questions about the test before we dive in on actually doing some of this stuff? Open everything just like normal. 50 minutes, do your test, scan it, submit it to me, just like you submit homeworks. A+. Go out into the world, except don't, and cheer and hooray, it's over until the fall. And my Perrier stock is getting low. If anybody wants to send me Perrier, 716 East Ogden Avenue, apartment 209. There you go. You can send me a case of Perrier. That'd be great. Just kidding. Don't do that. Earn your hard-earned student money on ice cream. All right, so here we go. Let's do some damn dynamics. First, we'll start with a 4-bar linkage, and we'll look at this particular problem here. Let's just do number 6. I've asked you on this review guide to do the kinematic analysis, not the algebraic method. You saw the algebraic method is kind of long and arduous and takes a lot of calculation, right? So this is like calculating the K1 through the K5, the capital A through the capital D, all that stuff. That sort of lends itself well to computation, right? If you're doing this in MATLAB. But when you're doing it by hand, it's really not the best because it just kind of takes forever, as you saw when you did the hand calculations for your simulation. So this is why I'm giving you this kinematic analysis idea in doing it this particular fashion. All right, so we'll go forward and we'll do the kinematic solution here. When it comes to the test tomorrow with your linkage problem, do whatever the hell you want. All right, you punch it into MATLAB to verify your answers. You have to show me on paper at least how you would sort of do it on paper. So give me enough information on the paper. If you want to punch it into MATLAB, check your answer, fine with me. All right. You want to do the kinematic solution? Fine. You want to do the algebraic solution? Fine. All right. You just got to show me what you're doing on paper so that I can follow you. Okay. So that's that. Let's get to it. 4-bar linkage has lengths. A is 5 inches, B is 2 inches, C is 5 inches, D is 4 inches. Drive angle given 80 degrees, drive velocity 25 radians per second, and we're given angles of theta 3 and theta 4. And what is the crossed configuration? It's the analysis we're going to do here. we want to determine the magnitudes of the linear velocities of the pins at A and B. All right, so that's the analysis that we're going to do. So I'm going to get V over to the white pad then, and we'll get on with it. My dog's looking at me funny. What are you doing? Okay, here we are. So this is number 6 in the review problems. All right, so it's a 4-bar linkage with the following information. We have this little a, which is sort of like the first driving link, is 5 inches. Little b is 2 inches. Little c is 5 inches. This is link number 3. And the distance between the pinned points, which we give the variable little d, is 4 inches. The drive angle, theta 2, given as 80 degrees. The drive angular velocity, omega 2, is 25 radians per second. The angle theta 3 prime, this is primed because we're in the cross configuration, was given to us as negative 113.5 degrees. And the angle theta 4 in the prime configuration or the cross configuration was given to us as 141.8 degrees. All right, might be nice or helpful to kind of like make a sketch of what this actually looks like, just to remind ourselves our 4-bar linkage. All right, so down here we call this point O2 because oxygen, I don't know. Over here we call this O4 because ozone plus oxygen, I don't know. All right, we know the distance here is 4 inches. It's related to the distance little d between these two guys. All right, so there's your 4 inches between those two pieces in the chain. And so let's draw our linkage assembly. All right, so we've got 5 inches for the first link in the chain, 5 inches. So it's going to be slightly longer than this, maybe about that length, but it's at an 80-degree angle. So maybe up here is probably a good spot, a good approximation for the first link in our linkage. And we're told here that this is 80 degrees. All right, up here, this is point A. All right. Next link in the chain is link B. It's 2 inches in length, and we're told that it's at an angle with the horizontal of negative 113.5 degrees. All right, so that's kind of what we're going to do next. Here's the horizontal, and it's at negative 113.5, and it's 2 inches. All right, so I know that this angle here is 90 plus 10, so this is 100 degrees in the negative direction. So I need to go another negative 13.5 degrees from there for my next link in the chain. So the next link in the chain, 2 inches in length, maybe looks something like that. All right, so here's point B. Finally, we're going to look at the third link in the chain, which is link C. This is at an angle of 141.8 degrees. So this third link has to connect up with point O, O4 that is. It's my graduating high school year. You think I'm kidding about that? But yep, I'm that old. And there we go. We're told that this angle theta 4 is 141.8 degrees, and this looks like it could be about right. So that seems reasonable to me, about 141.8, so I like that. All right, the length here, this is 5 inches. This guy also 5 inches, my first link in the chain, and this guy here is 2 inches, as a reminder. All right, so there's a little sketch. It's kind of in this crazy cross configuration. It's all like confuddled and crazy, but that's sometimes how these linkages are. All right, so we're asked then to find in this particular configuration if the angular velocity of this guy around the horn is 25 radians per second, then what is the velocity of point B and the velocity of point A? All right, that's what we're looking for. And we'll use kinematics. All right, so when you're going about the kinematic solution, it's really kind of the 4 magical equations that we can use to kind of relate everything together. So we'll use the 4 equations here, which is that the velocity of A, kind of all fixed axis rotation equations, is omega 2 cross the position vector which locates A from O2. We have that the velocity of B relative to A is the angular velocity omega 3 crossed with the position vector that locates B from A. We have the velocity of B is equal to omega 4 crossed with the position vector that locates B from O4. Okay, that's locating B from my second pin. And you also have the relative velocity equation that the velocity of B is the velocity of A plus the velocity of B relative to A. So these are your four magical equations that can bring everything together for you in the kinematic solutions. So here we have 1, 2, 3, and 4. So we're going to use each one of these equations. And once we make our way through and go through all those equations, we'll figure out angular velocities, and that will in turn give us linear velocities. All right, so away we go. First is equation 1, which is that the velocity of A is the angular velocity omega 2 crossed with the position vector that locates A from O2. All right, we've done this a lot now, so I'm going to move pretty quickly. Hopefully we can sort of understand where all these things are coming from relatively quickly. The angular velocity of the second link in the chain, this is given to us. So it's my drive angular velocity. It's 25 radians per second. So this is 25 k hat radians per second. I'm crossing this with my position vector that locates A from O2. All right, so that's the position vector associated with this second link in the chain here. All right, so that's got a total length of 5 inches, and it's at an angle of 80 degrees. So it's going to be, after all said and done, my position vector is 5 inches times the unit vector which locates it, which is cosine of 80 degrees I hat plus sine of 80 degrees J hat. Everything is known on the right hand side here, so just do the hokey pokey and cross product yourself around. Negative 123 I hat plus 21.7 J hat. Units here are inches per second. Remember, units are important. Inches per second, not football fields per second. Darn, right? So you could convert to football fields per second if you want, right? Football field, 120 yards long, 36 inches per yard, 36 inches times 120 yards. Boy, that's more math than I care to do right now. All right, be like 2880, I think, is the right number, approximately. All right. Right, so there you go. There's your velocity at point A. That part is easy. The next bits are where it gets a little bit more complicated and a little bit more confusing. Does someone have a question? No, just that the meeting has started. Okay, good. Next, we go to equation 2, which is the relationship between kind of pretending that point A is a fixed point and looking at how B moves relative to A. So we sort of assume that A is fixed and look how B moves relative to A. So we have this idea that the velocity of B relative to A is the angular velocity of this third link crossed with the position vector that locates B from A. All right. I don't know omega 3. I know that it's healthy for me, a lot of fish oil, but I don't know the angular velocity here, omega 3, so I got to keep it as an unknown. Crossed with my position vector that locates B from A. All right, well, that link length is 2 inches, and that's at an angle problem, which is something like cosine negative 113.5 degrees I hat plus sine negative 113.5 degrees J hat. Ooh, running out of space a little bit. All right, so there you go. After the dust settles here, your cross product's going to be done by keeping omega 3 as an unknown in this portion of the problem. You'll end up with something like 1.83 omega 3 I hat minus 0.80 omega 3 J hat, still which is units of inches per second, assuming that omega is in radians per second. All right. So here, this is utilizing equation number 2. We'll have to sort of keep this for now. We don't know what omega 3 is, but we'll just keep plowing through with our analysis and see things sort of settle out in the future. All right, equation number 3 here, we have that the velocity of B is equal to the angular velocity of this fourth link crossed with the position vector that locates B from O4. All right, so here we're looking now at what's going on with this particular link. All right. So it's 5 inches in length at an angle of 141.8. And so we can use that to define the position, but we still don't know what the angular velocity of that link is. So we have to do something like omega 4 k hat, again, omega as an unknown, plus the position vector here now, total length of 5 inches, and the unit vector that defines it is cosine of this angle 141.8 degrees I hat plus sine 141.8 j hat. After everything settles, velocity of B, negative 3.09 omega 4 I hat minus 3.93 omega 4 j hat inches per second. We'll call this equation 3. All right. So still, we don't know omega 3, we don't know omega 4. So we just have to keep moving. Keep on keeping on. We'll go to equation 4, which is our relative velocity equation. The velocity of B is the velocity of A plus the velocity of B relative to A. So now we're going to start plugging things in. All right, the velocity of B, this here is coming from number 3. Velocity of A comes from number 1, and the velocity of B relative to A comes from number 2. So we have all of these pieces, we just got to plug them all in. All right. So the velocity of B, negative 3.09 omega 4 I hat minus 3.93 omega 4 j hat, going to be equal to the velocity of A, which we solved for up at the top, negative 123 I hat plus 21.7 j hat, and then add to that the velocity of B relative to A, 1.83 omega 3 I hat minus 0.80 omega 3 j hat. All right, units on all this, inches per second. Here now we have 2 equations, and we have 2 unknowns. So we have 1 equation in I, 1 equation in J, and our 2 unknowns here are omega 3 and omega 4. So we can kind of solve these together now and determine the angular velocities omega 3 and omega 4, which will help us solve the linear velocities. So we have something like I hat is going to be negative 3.09 omega 4 equal to, here this component, negative 123, and this component, 1.83 omega 3. Right? Similar idea for the j hat direction. That was a terrible j hat. I should purchase like hats. It's like a I hat and a j hat. Yeah, I think that would be funny. It's like if we're working in the I hat direction, I put on my I hat. I think that'd be good. The new Apple product, I hat. All right. Negative 3.93 omega 4 equals 21.7 minus 0.80 omega 3. All right, so these are pulling off the j components here, here, and here. All right. So we got 2 equations here, 2 unknowns. I trust your powers of math, though sometimes suspicious, can solve these together. I believe that you can do this. Put it in your calculator, put it in MATLAB, solve it with the substitution method, solve it however you want. All right, go to the Googles and use an equation solver. I don't really care. All right, you'll end up with values for omega 4 and omega 3. It looks something like omega 4 is 6.0 radians per second, and omega 3 is 56.9. So there you go. Those are your angular velocities. It's not really what we're after. We're after the velocity of point B, but these are nice intermediate steps that help us get there. And that's because if we plug this guy back into our equation for the velocity of B, which is equation number 3, here, we can solve for the velocity of B using this guy. All right. So finally, we have that the velocity of B, after we plug things back in, is going to look something like negative 3.09 times omega 4, which here is 6 radians per second, I hat, minus 3.93 times omega 4, which again is 6 radians per second, and the j hat. So you'll end up with a velocity at point B, and again, this is inches per second, that looks something like negative 18.5 I hat minus 23.6 j hat inches per second. There we go. Rawr. Did it. Questions on this method. So we looked at the kinematic method. You've done the algebraic method quite a bit. You've written code in MATLAB, a function in MATLAB. If you want to use that to verify your answers, not a bad idea. When it comes to the test, you have to show me enough information on a piece of paper to tell me that you know what you're talking about. All right, so you can't just be like, I punched these numbers into MATLAB and this is what I got. Okay, that ain't good enough. All right, you got to tell me how you did it. What are the numbers, so on and so forth. All right, questions on this problem? Okay. Well, if there's no questions on this problem, let's move on to the last problem that I want to work on, which is the gearing problem. So you got a couple gear problems kind of on your test, or sorry, on your exam review sheet here. I like number 9. This is a reverted compound gear train. You guys built your own 3-stage compound gear train for the homework. So you're all experts in compound gear trains with multiple stages. You can pull out multiple gears and make these assemblies now. You're pros at that now, okay? Let's look at number 9. I like the reverted compound gear train. It has this additional like restriction that is the center to center distance between the counter shaft and the main shaft have to sort of be the same. And that kind of like makes things a little more interesting. So we'll work through this problem and go through it. All right, so this is number 9. Engine, number 9. Going down Chicago line. Okay, so this is our reverted compound gear train. All right, and we're given in the problem some information about this particular train. We know that the gear ratio is 65 to 1. Right, so 65 to 1. There's no negative sign here, so whatever input direction is, we're going to have the same output direction on the shaft, and you can kind of see that in the picture here, so that's a good thing. 65 to 1, meaning I give it 65, it gives me back 1. So the input to the output is 65 to 1. All right, so keep that in mind. We're told that the number of teeth on gear number 2 is 22. The number of teeth on gear number 5 is 150. And we're also told that all gears have same diametral pitch. And remember, diametral pitch, P, is number of teeth on the gear divided by the pitch diameter of the gear. And for this particular problem, P is equal to 8. Units here are inches inverse, actually, for pitch diameter and for diametral pitch. And a lot of times you'll just see diametral pitch reported with a singular number, like no units after it. But diametral pitch actually does have units. It looks something like 1 over inches or 1 over meters. And that's because this is a pitch value. Pitch is usually given with units of 1 on length. It's telling you how many things there are per length. In this particular situation, it's how many teeth there are per length. When it's talking about a screw, what is the pitch of a screw? You might see like a 1/4-20 screw. That means that there are 20 revolutions for every inch of length of that screw, right? 1/4-20. There are 12 revolutions of the teeth on the screw per every inch, right? So talking about the pitch, that's usually given with units of 1 on length. Though usually pitch is just given as a number, there is actually a unit associated there. Okay, enough espousing. Let's, as they say in Mulan, let's get down to business to defeat the Huns. Man, you guys probably don't even know what I'm talking about. Sometimes my jokes, like, I don't even know if they just land or if they're just like right over the top. Like, nobody gets them. All right. It's like, I don't know about you, but I'm feeling 22. Okay, you guys probably all get that one because you know Taylor Swift. But let's get down to business to defeat the Huns. Man, maybe one person gets that. Maybe. Okay. All right. So let's get down to business. And we want to find the center to center distance between input shaft and counter shaft. All right. Mulan, my favorite movie. No, just kidding. My favorite movie, you guys know this. It's Titanic. Come on. I don't even know what my favorite movie is. Guys, ever seen Pacific Rim? Man, that movie is crazy. I just watched that a couple days ago. That movie's ridiculous. Okay, go watch Pacific Rim if you haven't already. That movie's nuts. All right, let's get on with it. So our fundamental law of gearing says something like 1 divided by the gear ratio is the same thing as the velocity ratio, which is the output versus the input ratio. So in this case, that's omega 5 over omega 2. What is the output of the system given an input? And we know that this particular ratio, because of the first fundamental law of gearing, is a combination of the product of the teeth on the driving gear divided by the product of the teeth on the driven gears. In this particular setup, that is N2, N4 over N3, N5. All right. You got to know this. This you got to know for the test. Something that looks like this, if you're going to build a compound gear train, you got to know first fundamental law of gearing. That's probably the most important takeaway from this portion of the class. So you can bet that something like that's going to come up. All right. Got to know it. You gotta. Right. So if we punch in numbers for our problem, this looks like 1 on 65, which is our gear ratio, is going to be equal to N2, we're given as 22 teeth, just like all of you have, divided by N4, which we don't know. N3 we also do not know. And the number of teeth on gear number 5 is 150. So we're going to rearrange this so that we can come up with a relationship between the number of teeth on gear 3 and gear number 4. This is going to help us determine center to center distance because we're going to need to know the sizings of the gears by calculating numbers of teeth on each one of the gears so that we can determine the center to center distance. You come up with a relationship here that is something like the number of teeth on gear number 3 is equal to 9.53 times the number of teeth on gear number 4. We're going to call this equation number 1. Now, usually if you have a relationship that looks like this, you might want to be a little suspicious. When you're talking about numbers of teeth on various gears, you probably want to look at whole numbers as a relationship between the numbers of teeth. All right, so 10 times the number of teeth on this gear as there are in that gear, or 1/4 the value. Here we have something like 9.53. A little suspicious. Usually you don't like to see decimal values there that are something like that. Okay, but let's carry it through and let's kind of just see what happens. Maybe if you want to carry the fraction, that can be a little bit better. Usually it's better to deal with gear analysis in terms of fractional values, but let's just roll with this for now and sort of see what happens. But usually if you get some crazy decimal equivalence between, gear numbers, it should be suspicious because we know that these gears all have whole numbers of teeth. No half teeth on these gears, or they're not going to work very well. Okay, so this general relationship we have, but we need one more relationship, and that is the constitutive relationship that the distance between the shafts has to be the same. So also, center to center distance must be equal for 2 to 3 and 4 to 5. So what I mean by that is the diameter of gear 2 plus the diameter of gear 3 has to be the same as the diameter of gear 4 plus the diameter of gear 5. Okay? Otherwise, your gears aren't going to mesh somewhere. All right? That relationship must hold because the distances between the shafts has to be consistent. All right? So let's recall that there's this relationship between pitch diameters and diametral pitch and number of teeth. And that is that the diametral pitch is equal to the number of teeth divided by the diameter. Or if you want to rearrange this, you could say that the diameters of each one of these gears is equal to the number of teeth divided by the pitch diameter. All right. So since there is a sort of direct relationship here between number of teeth and the diameter of the gear, and all of the gears in this assembly have the same diametral pitch P, then you can write the direct relationship, which is that N2 plus N3 is equal to N4 plus N5. And that's only if all have same diametral pitch P. If they didn't have the same diametral pitch, then you wouldn't have the same general relationship, okay? And that's because if you plug in like this relationship over here that D is N on P, if they all have the same P, then that P will cancel and you'll just be left with a bunch of N's. Otherwise, you might have something like here, the diametral pitch of gears 4 and 5, and here normalizing the diametral pitch of gears 2 and 3. But in this particular problem, since we know that they're the same, okay, bye-bye. Like, you can just cancel this out directly. Hopefully we're all sort of following that. All right, so let's then punch in information that we know. We know that we have gear number 2 has 22 teeth. I don't know about you, but I'm feeling 22. I'm going to use the relationship that I solved up here. This relationship number 1. So here we have 9.53 times N4. This is equal to N4 plus N5, which is 150 teeth. And you can come up with that the number of teeth on gear number 4 is going to be 15. All right, so an interesting finding. Plug this back into 1, and you'll get that the number of teeth in gear number 5, and this is, sorry, not number 5, number 3. And this is where things are a little strange, but here we get 143 teeth. And the teeth on a gear should be some integer value. So if you're getting something like 2.7 teeth, okay, well, that ain't right, all right? You should be expecting something more than that, some positive integer value for the number of teeth, all right? So there you go. Number of teeth on gear number 3 and gear number 4. We're not quite done yet. We still need to determine what the center to center distance is, okay? So still need center to center distance, which we typically use the variable delta for that center to center distance. The center to center distance, you could use the distance between the centers of gears 2 and 3 or the centers of gears 4 and 5. Doesn't really matter. We'll here have, let's use 2 and 3. Oh, sorry. The center to center distance will be the radii of the 2 gears that are in contact there. The diameter of 2 divided by 2 is the radius, plus the diameter of 3 divided by 3, or divided by 2 is the radius of that 3rd gear. And the diameters, remember, are related to diametral pitch. And then we have that D is equal to the number of teeth divided by the diametral pitch P. So here, number of teeth on gear number 2 is 22, divided by the diametral pitch, which is 8, divided by 2. And plus number of teeth on gear number 3 is 143 teeth, divided by the diametral pitch is 8, divided by 2. Okay, so here we're using D is equal to N on P, remember? So ultimately, you solve this guy together, and you'll end up with 10.3125 inches as my center to center distance, or if you want to use carpenter language, 10 and 5/16 inches is your answer. So there you go. Bam! That's it. That's all you get. Yes. Any questions? There you go with your gear train analysis. And I'm glad that I look at the comments now. I'm glad you guys are with me on the Mulan quotes. Eddie Murphy's in that movie, man. He voices the dragon. It's awesome. Okay, well, if there's no questions, make sure you come a little bit early tomorrow. Get all your stuff prepared. Get ready. Take it to town. Crush exam number 3, and that'll be it. All right, you guys are all done great. Proud of you guys, sticking through to the end. So good job, and we'll see you tomorrow.